Hey everybody, welcome back to another lecture video. In this chapter, we're going to be going over carboxylic acids and esters. So let's get started. So the main functional group in carboxylic acids is what we call the carboxyl group. And the carboxyl group consists of the carbonyl and the carbonyl carbon being attached to a hydroxyl. So that's altogether going to be the carboxylic acid functional group. So the goal here is to write IUPAC names, common names, and to be able to draw structural and line angle formulas for these carboxylic acids. So just to start off, in the IUPAC system, we take the ending of the parent chain, we drop the letter E, and we replace that with oic acid. So methane, CH4, we would drop the E, it would be HC C double bond O, OH. So a one carbon methane becomes methanoic acid. Ethane becomes ethanoic acid. Propane, propanoic acid. Drop the E, add oic acid. When it gets time to number anything, any substituents, remember that the carbonyl carbon is the number one carbon. So moving away from that, this would be 2, this would be 3. So 2-methyl propanoic acid for a substituent. A couple more substituents here. Benzene, we can take benzene and add a carboxyl group to it. That makes benzoic acid. So benzene doesn't exactly have the same name change, but benzene becomes benzoic acid. If we have two substituents on benzene, we can call them by their numbers. 3, 4 in this case, benzoic acid, dichloro, sorry. The number 1 carbon on benzene is going to be the position of the carboxyl. And just like we did with benzene, if we only have two groups and if there's only two groups, we can say that they are ortho, meta, and para, depending on where they are positioned next to each other. So here, the number 1 carbon for the carboxyl group and the number 2 carbon for the bromo means we have an ortho situation. So instead of saying 2-bromobenzoic acid, we could say ortho-bromobenzoic acid. Carboxylic acids do have common names, and many are still called by their common names. There's some prefixes. So for 1 carbon, 2 carbon, 3 carbon, and 4 carbon, we get some different prefixes than you're used to. Form for 1, acete for 2, propion for 3, and butyr for 4. So for example, this is a 4-carbon carboxylic acid. We would call this butanoic acid, but we could call this butyric acid. Butyric acid. So butyr, and then we add ic acid to it. In addition to common names, we have a common numbering system. This involves using the Greek alphabet. Alpha carbons are identified as the carbon directly next to the carbonyl carbon. And then we move away from there. Alpha, then beta, then gamma, then delta, epsilon, whatever. So old naming system for carboxylic acids. A red ant, for example, contains methanoic acid or formic acid, as we better know it. This is the defense of the ant that stings our skin. Sour taste of vinegar is due to ethanoic acid, right? We know this better by its common name, acetic acid. So we add that to water, we get vinegar. All right, learning check. Give the IUPAC and common name for the following carboxylic acid. Don't forget to identify the longest chain, replace the E in that alkane name with oic acid, count out any substituents. All right, pause it, give it a shot. Hopefully you came up with 2-methyl propanoic acid. You could have also come up with beta-methyl propionic acid or 2-methyl propionic. So common name, common numbering. Give the IUPAC name for each of these compounds. So again, carboxylic acids, one's a benzene derivative. Pause it, give it a shot. So hopefully you come up with 3-methyl butanoic acid for your first one, and 3-bromobenzoic acid, or meta-bromobenzoic acid. You could also have called the previous one beta-methyl butyric acid. One more learning check. Draw the line angle formula for 4-chlorohexanoic acid. So 2, 3, 4, 5, 6. So mine's upside down now. Guess I'll make it this way. So 1, 2, 3, 4 says we have a 4-chlorohexanoic acid. I think mine's backwards from this one, but good. So alpha hydroxy acids, as we call them, AHAs. These are found in fruits, milk, sugarcane, so found naturally. 2 L's in naturally. They also naturally occur, these are naturally occurring carboxylic acids that have a hydroxyl group on the carbon atom adjacent to the carboxyl, aka on the alpha carbon. So alpha hydroxy acids have actually been used by dermatologists in concentrations as high as like 20 to 70%. And they use these things to remove everything from like acne scars, and they use them in skin peels to reduce irregular pigmentation. They use them for age spots. And I've got a list of some of these alpha hydroxy acids here in a second. Now, these are natural ones. Now, how do we get them? We get them from oxidation. Remember, primary alcohol oxidizes to an aldehyde, oxidizes to a carboxylic acid. On Thursday, remind me to tell you about my story. I have an issue that happened to my mead that I was making where this exact sort of oxidation started happening. Now, these alpha hydroxy acids, as I mentioned, there's several different alpha hydroxy acids that we can actually find in skincare products, either used singly or in combination, but you can see a few of them here. Maybe you even know the names of some of these. But in all of these cases, there is a alpha hydroxy. This one's a dicarboxylic acid. Yeah, alpha hydroxycarbons. Okay, moving on. Let's talk about properties of carboxylic acid. So, carboxylate salts are often used as preservatives. So, carboxylate salts. We'll talk about how we prep these in a minute. But they're often used as preservatives and flavor enhancers in soups and seasonings. One of the examples is sodium propionate. This is a preservative. It's added to cheeses, bread, other bakery items. It inhibits spoilage of the food by microorganisms. So in this part of the chapter, our goal is to talk about boiling points, solubility, dissociation, and neutralization of carboxylic acids. So, carboxylic acids are strongly polar because they have 2 polar groups. They have the hydroxyl group and they have the carbonyl group. And you should remember both of these are polar and little dipoles, charge separation. The OH here also lets hydrogen bonding happen, the same stuff that we saw in the alcohols, which gave alcohol such a high boiling point. If we compare them, we can actually see here something like propanal, which contains the carbonyl, one propanol, which has the hydroxyl. Now just comparing those, we see the hydroxyl is stronger, has a higher boiling point, meaning it's harder to break those bonds, to separate our molecules into a gas. 49 degrees for the aldehydes, 97 degrees for the alcohol. Combine those two groups and we get a molecule that is so hard to pull apart from itself that the boiling point needs to be 118 degrees Celsius. This is a higher boiling point than water. Excuse me. So ethanoic acid, or carboxylic acids in general, are going to have higher boiling points than alcohols, ketones, aldehydes of similar mass. And I forgot to mention that all of these masses are roughly the same. So we can kind of eliminate the effect due to mass and just see the effect due to the groups. Now, one of the other things that leads to the high boiling points of carboxylic acids is that they can form something we call dimers. Now, these two hydrogen bonds between the dimers form between the between the carboxyl groups. The carbonyl group of one to the OH of the other, carbonyl group of the other to the OH of the other. So, what this does is it effectively doubles the mass of the molecule, and then that just increases the temperature needed to reach boiling point. So, in addition to being very polar, this situation happens. These dimers form, and you can see how they attract each other. So this is also adding to that molecular Velcro that drives the boiling point up. Quick learning check. So match each of these compounds by name to the temperature at which they boil. So one of these boils at 141, one boils at 100, and one at 36 degrees. So pause it, give it a shot. Hopefully you would have said that pentane, being the alkane, has the 36 degree boiling point. The alcohol would be 100, and then the largest boiling point there had to belong to the carboxylic acid. Excuse me. Alright, carboxylic acids are soluble in water for a few reasons. They can form hydrogen bonds with water molecules. Not just one, but many. So you can see here a water molecule forming a hydrogen bond to this carbonyl, another water molecule to the carbonyl, another water molecule to the hydrogen of the OH, more water molecules to the lone pair electrons that are on the oxygens in that OH. Lone pair electrons is what I'm drawing in. So lots and lots and lots of bonding. 1 to 5 carbon atoms, carboxylic acids, with 1 to 5 carbon atoms are very soluble, and then they get less soluble as the number of carbons actually increases, typical of most of the other molecules we've looked at. Carboxylic acids are also weak acids. They're not strong acids, meaning that most of the time, if we put an acid into water, it doesn't completely convert into this. The majority of it, this is just to give you an idea. At equilibrium, we may have 10% ionized ethanoic acid and 90% just still unionized. So it's not a strong acid in that it completely breaks apart, but they are stronger than, I guess there's a whole range of acids, and we don't know enough of the types of acids yet to be able to classify these. Anyways, they're weak acids. They do dissociate in water, and they do produce what we call carboxylate ions. Carboxylate ions are what happens to a carboxylic acid after it loses its H. They also get their different name when that happens, and we need to go over that. Now, acids can lose their proton because the 2 oxygen atoms in the carboxylate ion stabilize this negative charge. You can see it here. This negative charge is because there's a bunch of lone pairs sitting on this oxygen, but they could drop down, form a double bond, kick this out, and then this oxygen up here would be the one with the negative charge, and then it goes back and forth, just like benzene. So this is a stable kind of arrangement here, more stable than some other acids. So there we go. So when we lose an H, our carboxylic acid becomes a carboxylate ion. Carboxylate is just the category or the technical term. Ion is always included because there is a charge. But for example, acetic acid becomes acetate. Methanoic acid would become methanoate ion. So O8 ion is what we're adding. O8 ion. What's another one? Butanoic acid would become butanoate. And actually, we used that one earlier. Sodium butanoate, I thought. Oh, sodium propanoate. Sodium propanoate. We said at the beginning of this section. Propanoate. Sodium, but propanoate. So what would that look like? It would be a propanoic acid that lost its H, so it has a negative charge. And all of these acids that lose their charge, or I'm sorry, that lose their H's, they have to be now paired with a positive ion. So that's why you'll see them as salts, sodium propanoate or potassium ethanoate, and so on and so on. So here we don't show it paired with anything, but in the preservative world, you'll find it as a salt. Okay, let's some more examples. So methanoic acid, ethanoic acid. Here you can see some properties of just some carboxylic acids as they get longer, sort of a summarizing table. Boiling points go up as the chains get longer. Solubility goes down as the chains go longer, and then their strength as an acid. You can see here as they get bigger, their acid strength actually goes down. So an acid dissociation constant is a measure of how much acid there is at equilibrium. A number like this, 1.8 10 to the minus 4, is a small number, but 6.4 10 to the minus 5 is a smaller number. So it's actually a larger number towards the top here, if you can tell. Smaller exponent means larger number. So in this case, as we get longer and longer acids, they become less and less acidic. The smaller ones are the most acidic. And that might have to do with stabilizing that charge. All right. Let's write a balanced equation for the ionization of butanoic acid in water, and we'll identify the carboxylate ion. So the way we do this, we're just going to add water to this formula. We know we're going to get H3O+, that's the acid molecule. So whenever water is around, water can act like a base. If this is the acid, this is the base. And it'll gain the hydrogen, and the acid will lose the hydrogen. So we'll have H3O plus CH3, CH2, CH2, C double bond O, O minus. And butanoic acid should become butanoate ion. Or in other words, a carboxylate ion. So there's one more situation where this happens. So this was adding to water. Things ionize in water. Things dissolve in water. Acids dissolve in water because this happens. They become more likable to water. Now, we already know carboxylic acids are good in water, but this is part of the reason they dissolve so well is because they do react with water in this fashion. But we can make them even more soluble. I mentioned that most carboxylic acids don't completely ionize. Well, let's take a look at how we can actually force that to happen. So we can neutralize the acid. This converts all of that acid into its carboxylate ion. And we can make carboxylate salts. These are the product of neutralization of an acid. with something like a strong base, like sodium hydroxide or potassium hydroxide. Now the carboxylate ion is just again replaced or made by replacing the ic ending with that 8. So instead of oic, it becomes O8. I guess that's better. Minus ic, add 8 ion. Ic acid, add 8 ion. So here we can see methanoic acid. Highlighted is the water that forms from the neutralization. Whenever you neutralize acids with bases, or bases with acids, you always form water and a salt. So we're always going to get a water product here, and we'll get a salt product. The salt will be named based on what ion was paired in front. So in this case, methanoic acid will become methanoate, but it'll be sodium methanoate, or formate if you use the old name. Benzoic acid here becomes benzoate, but it's potassium benzoate because we mixed it with potassium hydroxide. If we had mixed it with sodium hydroxide, it would have been sodium benzoate. So neutralization is a lot like the ionization, except that where ionization produces an acid molecule and just the carboxylate ion, the neutralization produces the salt, which has 2 charged things in it, and water. So got to get those straight. All right, now carboxylate salts, these are ionic compounds, strong attachments between the metal ion and that carboxylate ion. These tend to be solid at room temperature because they're salts. They have high melting points, like a lot of inorganic compounds do. And they're usually soluble in water because of those charges. Water likes those charges. And I mentioned they're used as preservatives. Sodium propionate, a preservative added to bread, cheeses, bakery items, we talked about that. Sodium benzoate, this one's added to juices, margarines, relishes, salads, jams, and this one inhibits the growth of mold and bacteria. There's even this one. This is monosodium glutamate, MSG. You may have heard of this before. It's gotten a bad rap. This is added to meats, fish, vegetables, bakery items. It enhances flavor, but it can cause headaches in some people. So that's MSG, monosodium glutamate, and you can see here it is made from a carboxylic acid that's reacted with some sort of sodium hydroxide to yield the sodium salt. And this is monosodium glutamate because you could add a second sodium to this side. There's 2 sides where this can happen. All right, we'll continue. So go ahead and write the equation for the reaction of propanoic acid with sodium hydroxide. So pause it, give it a shot. I would start off by actually adding in these guys, propanoic acid. All right, give it a shot. So again, the reaction should include the acid, the base, in this case the sodium hydroxide, the water neutralization product, acids and bases always make water, and a salt. So we should say it this way. If it's neutralization, you get water and a salt. If it's ionization, you get carboxylate ion and H3O plus. So 2 different products depending on what we're looking at. If it's a neutralization, you get one thing. If it's ionization, you get the other. But the carboxylate happens to both of them. The losing the H happens to both. Good. All right, I'm going to pause the video here and finish this in a second part. See you in a minute.